with just a couple of adjustments, we can get from a simple electron gun and a little bit of other apparatus the charge mass ratio of the particles that are in our cathode rays, which of course we know as electrons. And J.J. Thomson was able to find out that that charge mass ratio was absolutely huge when compared with the charge mass ratio of a hydrogen atom. And that's all he had to compare it to, because remember, that's all that had been kind of discovered, the idea of the atom. So the electron was a kind of new thing. And then if you think back to GCSE, he put that electron into his plum pudding model of the atom because the previous model didn't have electrons in it at all, and he'd obviously been able to isolate electrons. So it was this charge mass ratio where he was able to say this is a different particle that's clearly come from an atom, because the metal filament that we started with that's hot is made of atoms, and the electrons have come off of that. So this is why he's able to say it's a different particle. And as I say, he's also able to measure the charge mass ratio of it. Okay, so this is our electron gun. We've got our hot cathode connected to a low voltage supply just for the heating. Also connected to the negative side of our large potential difference. And then we've got this anode here with a little gap in it that's connected to the positive side of our large potential difference, about 5,000 volts between these two. And then electrons will leave this negative filament and go towards the anode, and they'll go through this little gap. And so this is our electron gun. So we've got this beam of electrons. And with that beam of electrons, J.J. Thomson managed to determine the charge mass ratio of an electron. There are two ways in which you can do that with this sort of apparatus. And there's also a third way that they might ask you about in exams, which is a bit of a fudge, and I'll explain that one last. So we'll start off with something called the cross fields method. If you put an electric field here, then what's going to happen to this beam of electrons? Well, let's say this plate's negative and this plate's positive. This beam of electrons is going to go up this way, parabolic motion. If then we want to straighten this out, we could straighten this out with a magnetic field. So Fleming's left-hand rule, the current here is actually going towards the electron gun. So that's why I've got my second finger pointing that way, because it's conventional current, so it's opposite to movement of electrons. We want the force to be towards the negative plate because we're trying to even this out and make it straight. So the magnetic field has to go into the desk here. So if I put on a magnetic field that goes into the desk here, then what happens to this beam? Well, it's going to straighten out. It will be straight when the force from the magnetic field is equal to the force from the electric field. So if I'm writing that out here, force from the electric field equal to the force from the magnetic field. The force from the electric field will be the electric field strength times the charge on an electron. And the force from the magnetic field will be the magnetic flux density times the charge on an electron and multiplied by the velocity of that electron. There's a little v here. We've got to be careful with our v's because we've got some big v's for voltage, little v's for velocity. We could actually get rid of this electric field strength and call it potential difference divided by distance. But this potential difference is the potential difference between these plates. It's not the potential difference for the electron gun. So I'm going to call it V D because we've got this D for distance here. Might be called other things in other places, but we can't just call it V because we're going to use that V for this potential difference later on. And I've got this E here for the charge on an electron. It's equal to magnetic flux density times charge on an electron times the velocity. And you'll notice that actually the charge on an electron just cancels. So we can't use this to find the charge on an electron. But this V, the velocity here of these electrons, well, the energy that we've given these electrons in the electron gun is going to be the potential difference. So energy is equal to potential difference times charge. That's the energy that they've been given, and that's all going to go into kinetic energy, so we can make that equal to a half mv squared. These v's are different, big V, little v. And I can say then that the velocity of these electrons will be the square root of 2 times the potential difference across the electron gun. So that's why I've had to put a little subscript here. Multiplied by the charge on an electron divided by the mass of an electron. So I've got this E over m, which is my specific charge, where specific charge comes in. And I can put this in here, and I can say that the voltage across these two plates divided by the distance between the two plates will be, run off the screen, the voltage across the two plates divided by the distance between the two plates is equal to the magnetic flux density times by the square root of 2 VE over M. So I know this, I can measure this, I know my magnetic flux density, we know everything, we know the potential difference in the electron gun. The only thing that we don't know is E over M. So we can work out the charge mass ratio. We can't work out the mass of an electron or the charge on an electron from this experiment, but we can work out the specific charge. And the specific charge is so different from that of other things, so atoms and ions, that it was quite clear this was a different particle. So that's the cross-fields method. There's another method that J.J. Thomson used. If we just get our electron gun, and we've got just a magnetic field now. So these electrons coming across here. What's going to happen to this electron in this magnetic field? Well, it's going to experience a force going down, and so the electron's maybe going to end up over here. And then this electron, well, it's actually the movement of this electron's this way, so the current's actually going to now be that way. So that my force isn't going to be towards the bottom of the screen anymore, it's going to be slightly to the left. And so my electron's going to move further around this way, and I end up with circular motion. So if I can get this beam of electrons going around in a circle, then I can make the centripetal force equal to the force from the magnetic field. If the electrons aren't moving fast enough, it will spiral in. If they're moving too fast, it may spiral out. But if I can adjust it so they're right, I can get the circular motion, and I can say that the centripetal force, mv squared over r, has to be equal to the force from the magnetic field. So I can then work out the specific charge again. The velocity here I can get from making the energy that we give the electrons equal to my kinetic energy equation, and I can find that actually V is equal to the square root of 2 V, this is the potential difference in the electron gun, E divided by M again, and I can then put this over here, and then I can rearrange to get E over M, the subject, and once I've done that, and I measure all these things, then I can find the specific charge on the electron using this. So this third setup is a bit of a fudge, and they do it, might ask you to do bits of it in an exam, but it's not possible to determine the charge mass ratio of an electron just using this method, because it involves knowing the velocity of the electrons or the kinetic energy of the electrons. And we know from what we've just done before that the energy we give these electrons will be the potential difference times by the charge on an electron, and we can make that equal to 1/2 mv squared. So to know the velocity, we have to know the charge on an electron, or even just to know how much kinetic energy they've got, we need to know the charge on an electron. So it's a circular argument, but they do sometimes ask about it. So if you've got an electric field, and our beam then, our electron beam, is going to bend up towards this positive plate. And if you start off with it going straight and then increase this potential difference and increase it until it just clips here, then we know actually that the electron has been in the whole length of this plate. We can call it L here. And we can start doing some SUVAT. So horizontally, I'm just going to call X, we don't actually know that much. Horizontally, we know that the velocity of the electrons is going to be the length of the plate divided by how long they're in the plate for. And so just for later on, it would be useful to say that the time they're in the plate for will be the length divided by the velocity. It involves knowing the velocity, this method, remember. Then vertically, the initial velocity is going to be 0, because all our motion is to the right here, and so there's none vertical. So that's going to be 0. The distance s is going to be half of the distance between the plates. I'm going to call this d. I normally call it d, but I guess you might not, there are other things you could call it, there's plenty of other letters. So the distance is going to be d over 2 from there to there, d over 2, but it's got to do in the time that it takes to get through the plates. We don't know what v is, but we're not really interested, don't care. The time, we already know, is going to be L over v. The acceleration is an interesting one. So the acceleration we can get from F equals ma. We can say that the acceleration is going to be the force divided by the mass, and of course the force is the electric field strength times by the charge on an electron. Divide that by the mass here. So we've got E over m, our specific charge, right? And that is the acceleration. So E over m. And so when we write out one of our CVAT equations, so let's go for S equals ut plus at squared over 2. This term we don't care about because u is 0. We know what S is, it's d over 2. A is the electric field strength times E over m, and you could say the electric field strength is the voltage between these two plates divided by the distance, but yeah, you could do if you wanted to. And the time we know from here, so we actually know everything apart from E over m, so you can use some data from this experiment to find E over m. I'm not going to do a video of me substituting in these things into here and then making E over m the subject. I'm sure you can work that out for yourselves, but this is how you might find the specific charge of an electron from this setup.